first of all, I'm going to start with the stuff you do know, which is from the previous lecture, to remember what we were discussing. We were discussing radiation from an arbitrary source distribution with a harmonic time dependence, and we're interested in the radiation fields. So what is radiation? Well, it's simply those fields in the Poynting's vector that are proportional to 1 over r squared. And this is because we're interested in the energy that radiates away to infinity, which completely decouples from the charge distribution. So we define the radiated power as the integral over a large sphere. Let's see. I also include the time average here because we have a harmonic time dependence, so we can just take the average over one period of oscillation. So time average like this. And if I say limit r goes to infinity, then it's the radiated power, because only the radiation terms will survive at infinity. And dA, well, that's r hat and r squared times 4 pi. That's the area of a large sphere. So so let's see, if this decays as 1 over r squared, then the r's cancel, and we get a constant radiated power when we integrate over the whole sphere. So that's how we separate the radiation terms from the non-radiative terms. So it essentially boils down to this. Okay, and the geometry we were interested in was the following. We have some source, which is has a length scale of roughly d, and we're interested in some point, let's say over here, which is far away, at r vector, and this is in the radiation zone. And the radiation zone is basically, well, to separate the near zone from the radiative zone, we use the approximation that d is much less than lambda is much less than r, which is the length of this vector, distance from the source. Okay, and if you don't recall how we determined lambda, that's basically k is equal to omega over c, and k is 2 pi over lambda. So that gives you the length scale. You could also say that kr is much larger than 1. That's equivalent to this. Okay. And the sources were on the following form. There's a spatial factor and a harmonic time dependence, both in the current and the charge distribution. Like this, okay. And the continuity equation boils down to the following when we make this assumption, and that is that rho is equal to I over omega, which comes from the derivation of this term, time derivation, and divergence of the current, which is the other term in the continuity equation. Okay, so the charges are localized; they stay in the same space, in the same place without moving. They're time harmonic, and they're finite, have a finite small extent. Small is smaller than both the wavelength and the distance to the observation point. The equation we're trying to solve is the equation for the vector potential in the Lorentz gauge. And we chose this because it's easy to find the, we're going to see that, but it's easy to find the electric field once you know the magnetic field. So we're just going to determine A, find the magnetic field, and then find the electric field. We don't need to explicitly find the scalar potential. And the Lorentz gauge was the gauge where we decouple the equations for A and V. Okay. Fortunately, we know the Green's function to this operator and the boundary condition that the fields go to 0 at infinity. So we can simply write down the solution of this equation in the following form. It is simply mu naught over 4 pi, then an integral over d3 r prime j of r prime e to I k r divided by r, where the big R is equal to the length of r minus r prime, and r prime, that's the integration coordinate, which simply points at the various places inside the source, and r is the observation point, same as always. Yeah, let's see, and there should be an e to minus I omega t, so I can write it like this: a of r, and then a of r t is a of r, e to minus I omega t. That's the complete solution. Okay. And we also found some approximations we could make. The first was that if I multipole expand 1 over r, like we did in electrostatics and magnetostatics, we found that there's only one term that goes like 1 over r, the small r. So if I write equals 1 over r plus order 1 over r square, and we recall that this will not give rise to radiation, because S is essentially the field square, and the fields are the derivatives of the scalar and vector potentials. So these terms cannot give rise to radiation. So I will just neglect them, because we're interested in the radiation field. Furthermore, we had this factor we could also approximate. So let's see if we can do that. E to I k big R we can approximate as e to I k small r, e to minus I k r hat r prime dot product. Okay, and this follows from simply expanding this r, which is let's see, r square minus r dot r prime plus r prime square. If you neglect this term here, which is of course going to be really small, and then Taylor expand in this term, which is small, then you get this. We did that last time, so I'm not going to go into more details unless there are any questions about that. No? It's fine? Okay. So let's go to this form of the potential and start expanding and approximating. Okay. So, okay, if you look at this form of the potential, I will now use the approximations to try to simplify this expression and get out the terms that are important. So A, let's see. So in the limit kr goes to infinity, which is the radiation zone, then A of r t is equal to e to minus I omega t, which is seemingly always there, mu naught over 4 pi r. Now I take the big R outside and make it a small r, because that's the only term in the expansion of big R which creates radiation. I have an integral over d3 r prime j of r prime e to I k r e to minus I k r hat r prime. Okay, this factor does not depend on r prime, so I can take it outside. And then we're left with this guy here inside. So I get mu naught over 4 pi e to I k r minus I omega t over r, spherical wave, and a factor, which is the integral over the charge distribution, d3 r prime j of r prime e to minus I k r hat r prime. Okay, now we notice that k dot r prime, that's going to be small because lambda is much greater than the size of the distribution. So if d is essentially the largest value that the length of r prime can have, well then k times r prime is going to be small. So we'll try to power expand this term here to simplify the integral. And all the other stuff is okay. That's not a problem. So you can expand the exponential simply as a Taylor series. So I'll write that down explicitly. R hat r vector prime sum from 0 to infinity minus I k to power n over n factorial, and then r hat r prime to power n. And here you see that if r prime dot k is small, then if you go to larger powers of n, they're going to be really small. Yeah, so we hope that this converges quickly. So we assume basically that the first term is going to be the dominating term in this series. However, sometimes there is a symmetry in the charge distribution which makes one of the first leading terms disappear. So you have to go to the first non-vanishing term. Okay, so we retain the first or the first few non-vanishing terms in this expansion when I put it into here and solve the integral term by term. Okay, so I'll write down explicitly the final answer for A. So I'll call it equation 1. Limit kr goes to infinity, A is equal to, let's see, our prefactors. And a sum. I move the sum outside the integral because now I can perform the integral term by term, which simplifies things greatly. And the integral we're left with is d3 r prime j of r prime and r hat dot r vector prime to power n. So now the only difficulty here is to find the first non-vanishing integral. So if the symmetry makes the integral 0, for example, then I have to go to the next term. Otherwise, I just keep the first one. So what we're now going to do is to examine some of the first few terms to see what does the radiation from the first and the second term look like, basically. And if you recall the radiation theory from quantum mechanics, you make essentially the same approximation there. So this should be known to you more or less. Okay, and to no surprise, the first term in this expansion is called the electric dipole term. And we're going to see why it's called the electric dipole term, and that's quite simple. If I write down now just the first term in this sum, then I have that A of R T in the radiation zone is equal to mu naught over 4 pi e to I k r minus I omega t over r integral d3 r prime j of r prime, because r hat r to power 0 is equal to 1. Okay, and if we recall from before that, let's see, we had that p of t, that's the dipole moment, was equal to p naught vector e to minus I omega t, simple harmonic time independence. And p naught, same as electrostatics, is given by d3 r prime r vector prime rho of r vector prime. We recall that we did this before, that if I perform a partial integration here, I could get a nabla on the j and an r vector. And because of the continuity equation, we remember that rho is equal to the divergence of j times a factor. So these integrals are actually the same, plus a factor, which is no big deal. So in the end, the electric dipole term simply looks like A of R T is equal to mu naught over 4 pi B of the retarded time over R. There you go. That's the whole thing. And this explains pretty well, I think, why this is called the electric dipole term, because it simply depends on the dipole moment of the charge distribution, does not depend on any of the higher order term in the multipole expansion of it. And we can also write this with an explicit time dependence, and with respect to the time now, not the retarded time. So let's write that out. A of R T can be written as an A of R that also depends on omega, if you want to be explicit, and then e to minus I omega t. And if we recall that p vector time derivative of tr, well, that's simply given by minus I omega p naught vector e to I k r minus I omega t. And here I just say that minus I omega tr, well, then I can expand that in terms of the big R, the distance from the source, right? As we did with the retarded time. And this gives us that A of R omega is equal to minus I mu naught omega over 4 pi. And here we see the explicit omega dependence, p naught vector e to I k r over r. And finally, when I insert into here, I get the e to minus I omega t, which gives me the time dependence. And I call this equation 2. This is the dipole, the vector potential from the electric dipole term. So this usually dominates this expansion here, and ordinarily the next term is only going to be important if for some reason this integral turns out to return something 0 or very small, so that the next term is important as well. Because as you can see, there is something that makes the next term small here, and also r prime to a large power also becomes small. So this is the first term that's important. It's ordinarily the dominating term. Now, we would like to know the fields from this charge distribution, and then we can simply use that H, the magnetic field, is 1 over mu naught curl of A And for the electric field, I don't go to the scalar potential and the vector potential. Rather, I use the Ampere's law. Which simply states that the curl of H is equal to minus I omega epsilon naught E. And this is because E has a harmonic time independence because the sources are harmonically time dependent, meaning that the time derivative of E is simply I omega. Question? Er det noe spesifikt? Korte trekk? Okay, so the question is what happened over here? Okay, so we start out with this integral. That's okay, right? That's the first term in the expansion over there. Okay, and now I just remind you that P of t is P naught, a vector, times e to minus I omega t. Right? That's, we assume the simple harmonic time independence for the charge distribution. So, well, if you want to insert P of t here, then you would get an e to minus I omega t. You could move it outside the integral because it doesn't depend on r prime, so that's pretty trivial. I also recall that P naught vector was d3 r prime, r vector prime, rho of r vector prime. And if I perform a partial integration on this one, well, then I get this term, this integral. Okay? This is actually, I think it's an exercise problem. At least it's a problem in the book. You can basically look at the integral, let's see, d3 r prime, let's say xj, for example, like this. If you perform a partial integration now on this, then perhaps there should be a divergence here. And now if you perform a partial integration, then you will get one term which is a boundary term which disappears. And this term turns basically into d3 r prime r vector when you gather the components again. This is x, right? So I need to gather all three components. So it should be x prime. And the divergence of j. We did this before, I think. So because of the continuity equation, we recall that, let's see, rho is something like I over omega divergence of j. And then we get back to this integral. There's an exercise problem on this in the book if you want to see the details. I can find it if you're really interested. So that's the magic behind here, but we did basically the same thing before, so well, you might not remember all those details. And then I could just say that, well, because this integral now was just this integral, and the I omega t is up here, well then this must be simply the dipole moment at the retarded time, right? Because in principle this is j at retarded time. No, well, there's some more basic algebra to get to this final expression, but that's pretty straightforward. Yeah. Here? No, I don't think so. No, it's not the derivative because this integral basically turns into this integral here, right? And then the I omega t part is already out here. This one. So this is the dipole moment. It's not the time derivative. And the I omega stuff you can take, well, you can take the I omega stuff inside as well, right? You can take away the derivative. Right, because when I take the derivative with respect to time here, I get down simply this factor in front. This is an eigenfunction to the time derivative operator, right? So I can take that factor back in again. So I don't remember exactly the tricks, but that's the final step there is quite trivial. Was that clear, or clearer at least? Okay. So as I said, if we're going to go through all the steps every time, then we're going to stay here for Christmas. So if you're wondering about the specific steps, it's good to ask. But yeah. Of the P? Here? Yeah, well, as I said, you can take away or insert I omegas as you want to take away the time derivative or get it down again, right? Because, let's see, rho of R t, which is proportional to P in the integral there. That's rho of R e to minus I omega t, meaning that dt of rho is simply minus I omega rho. So if I have a time derivative, I can divide by this factor to remove the time derivative, or, well, I can move the I omega around and the time derivative around as I want, because the time derivative is so simple. Okay, was that clear? Right. Now let's see. Back to the fields, I hope. So the Ampere's law states this. The time derivative here is also easy. It's just an I omega. And if I rewrite this, I can write that E is simply I over omega epsilon naught curl of H, or even simpler, I set naught over K curl of H. And set naught is simply a constant which I define as, let's see, mu naught over epsilon naught. It's simply a constant that shows up in many locations, so not much more magic than that. So when I want to find the fields now, I just insert equation 2 into equation 3. And I find the H field, and then I can find the electric field from the magnetic field without knowing the scalar potential at all. So for that reason, I haven't bothered to find the scalar potential explicitly. Let's see. Okay, so I'll clear some space, and then we'll have a look at the fields. But I won't go through the derivatives. I think you can do the curl just nicely yourself. The function is given here, if you want to play with the math. Let's see. So if I now insert 3 into 2, I will get out the magnetic field. So if I write down the result, which is simply taking the curl of a vector function, then I get ck squared over 4 pi r hat cross p naught e to I k r over r plus terms of 1 over r, let's see, terms of order 1 over r squared or higher. Okay, and there's a time dependence here which I suppress because it's basically everywhere. So if I now combine this with the lower part of equation 3, the Ampere's law, then I will get out the E field This is even longer and more tedious, but the procedure is straightforward. You just take some derivatives. So it's 1 over 4 pi epsilon naught, and then k square r hat cross p naught cross r hat e to I k r over r plus order 1 over r square terms. And if you want to see the rest of the terms, you can look at the lecture notes that are on the web. But I don't think it's fruitful to add those to the discussion because they don't contribute to the radiation. And those near fields are not going to be correct in our approximations anyway. Well, depends on the situation, of course, but in general not. And also here there should be a e to minus I omega t, but I suppressed that. Now, let's make some observations on this. The first is that because of this cross product with r hat, the magnetic field is always perpendicular to r. And this is in fact true for all distances, also if you include the higher order terms. Second observation is that at large distances, the E field is also perpendicular to R because of this cross product here. But as you know, there are some Coulomb-like terms here, which is going to give components of E that are parallel to R hat when you get close to the charge distribution. Well, actually, I should say there is a component that is parallel. And when I say small r, well, then we're in the, let's see, we have the approximation d much less than lambda much less than r. If I now just have d much less than r, well, then I'm going to have these parallel terms without the approximation breaking down. But basically, we're interested in this fact. So the electric field is perpendicular to the H field because of the curl here. And both of them are perpendicular to the r hat, as you can see from these expressions. So they form a right-hand system, just like the wave vector and the electric field and the magnetic field did for a plane wave. Let's see. And in the radiation zone, we can also write the E field as simply, let's see, Z naught H cross r hat. So they're all perpendicular. Now, to find the radiation pattern, we had to find the Poynting's vector, and that's the next item on the list. Let's see. So the Poynting's vector, S, that's defined as E cross H, and gives the energy transport, both direction and magnitude. So let's see, we should have a star here. And in fact, there should be a factor of half when we do the time averaging. But I skipped the factor of half just to get the pattern now, to see which directions have the most radiation. And because of this formula here, I can simplify this to only contain the magnetic field. So let's do that. Turns into minus H star. So I exchange the order, get a minus sign in front, and I get a cross product with H cross R hat. because that's the E field. Now, if we take out the Levi-Civita tensor and do some math, which I'm not going to go through, then you will find out that this is equal to minus h, let's see, and then h star dot r hat, that's one term, minus r hat h star dot h. You'll notice that this term is of course equal to 0 because of the fact that h is perpendicular to r hat, meaning that we're left with only this term, and that is simply equal to length of h vector times r hat. Let's see, and there should be a square, of course. Right? Because we remember that h star dot h is equal to h absolute value square. And this, again, is proportional to, if I write down now the h up here, and I get some angular dependence from this guy, this is proportional to, let's see, r hat cross p naught absolute value square over r square. So we get the correct r dependence, we get the radiation term, and then there should be an r hat. And finally, this turns into p naught square sine square of theta divided by r square r hat, like this. Because this cross product, well, that's basically the length of this vector times the length of this vector times the sine of the angle between them. And if that's how I define my angle theta. So if I have p naught and r hat, then this is theta, the angle between them. So I use the p naught to create my coordinate system, so to speak. So now we're going to define what the radiation pattern is. To make that explicit, so radiation pattern. Because that's one interesting thing we can get out from the Poynting's vector. So that is, let's see, the time average power, radiation power, let's say rad here perhaps, is equal to dA dot S over a large sphere, or it could be a different shape, but a sphere is convenient. And time average of S, let's say, this now turns into time average of S dot r hat r square d omega. That's the area element. Okay. I'm now going to refactor this, so I write it as the integral over omega. And I only keep, of course, the terms in S that actually decay as 1 over r square, so it cancels the r here, leaving me with dp d omega d omega. And this is the radiation pattern, the radiation from the source into a given angle. So if I compare these two equations, I can conclude that the radiation pattern is defined as C dp d omega time average is equal to time average of S and dot r hat. But at large distances, S is parallel to r hat anyway, so that's not a big deal. R square, like that. If I take this one away, I can just write it as, like, no, not the square. Just the absolute value of S, or the length of the vector, if you want. Now for the electric dipole term, if I compare to this expression here, well, the r hat, we knew that, and the r square, we multiply by that, meaning that dp d omega for an electric dipole is given by the time averaging. Now we did magically by using this complex notation, which we discussed before. So this complex notation actually takes care of the time averaging, leaving us with p naught square sine square of theta. Should perhaps be just proportional here. Okay. Now we can start to see what kind of shape this radiation pattern takes. We see that if we have a large dipole moment, that gives us a strong antenna or radiator. But we also note that if this is P naught, the radiation is going to the sides of P naught in a torus-like shape, as it did for the perfect dipole. So it basically looks something like this. And if this is theta, then this length is proportional to sine square theta. Okay? And this, as we discussed with a perfect dipole, this gives you the Brewster angle effect, that there's no dipole radiation in this direction here. Okay, any questions? Yeah. Also, as someone pointed out in the class, we could express this, both the fields and the radiation patterns in terms of time derivatives of the dipole moment. But I don't see how you learn much more physics from that. So you can look at that in the book if you're interested. But of course, it's the change, the time change in the charge distributions which give rise to radiation. And I think we take a 15-minute break now. And in the next lecture, we're going to discuss the magnetic dipole and the electric quadrupole terms, which are the next terms in our expansion for the vector potential.